The purpose of this screencast is to catch you up on material that we learned last week while you were in ISS. So right now I would like you to take out your tracker for the week and your worksheet from yesterday, if possible, and you're going to be working on the do now. Another thing that you're going to need is this sheet right here, which is your electronegativity chart, so you need to take that out as well. If you need one, please raise your hand at this point and Mr. T can give you an extra copy that we have. So we should be on your do now. Go ahead and pause the video while you complete the do now, and you're classifying these compounds as ionic, polar covalent, or non-polar covalent. So yesterday Mr. T told you that ionic compounds are 1.7 and above. Polar covalent compounds are 0.5 to 1.7. And then non-polar covalent are 0.0 to 0.4. So go ahead and pause the video now, and then unpause when you've finished your catalyst. Looking at the first one, the first compound is NaCl. So what I do is I find Na and Cl on my electronegativity chart, and I write down the values. So I've written them down here as 0.9 and 3.0 right here. Then I'm going to subtract my two values in order to find the difference. So we have 3.0 minus 0.9. At this step, I want to make sure that I subtract the smaller number from the larger number to get 2.1. Because it's above 1.7, it is going to be an ionic compound. And remember that ionic compounds are the most polar out of any kind of compound. I'm going to do the same thing for H2O. So I found H on my chart and it was 2.1. I found O on my chart and it was 3.5. I subtract the two, so 3.5 minus 2.1, and we get 1.4. 1.4 falls in the range of polar covalent because it's between 0.5 and 1.6. For the last compound we have I2, so there are two different I's here. So I find the electronegativity value for I, and it's 2.7, and we have another I, so it's also 2.7. When I subtract 2.7 minus 2.7, or any same numbers, I'm going to get 0.0. This means it's a non-polar compound. At this point, I want to check the question again, and it says, which of the following is the most polar? So ionics are going to be the most polar, so NaCl is going to be the most polar. So again, we're going to need this chart right here for the whole entire lesson. So if you were confused about where I was getting those values from, it was from this chart, and you can raise your hand to get the chart from Mr. T, or if you have any questions at all. So the homework for today for you to do is going to be to complete the worksheet from class. So if you don't finish the worksheet in class today, then you need to complete all the things that are in this packet, and you're going to be turning them in tomorrow for credit. This is our agenda. So we just took care of number 1. Now I'm going to be going through the notes with you one-on-one. Then you're going to be working on the worksheet. Okay? So the worksheet is going to be what you're going to turn in either at the end of class today if you're done, or tomorrow for homework. So our objective is to identify the intermolecular forces present based on the type of compound and investigate the effect of IMFs on properties such as boiling point, melting point, and bond strength. So the first thing that we're going to talk about are intramolecular forces and intermolecular forces. So now we're going to be on the top of your notes that you picked up or Mr. T gave you when you came in. Intramolecular forces are things that we've talked about before, but we haven't used this vocabulary word yet. Intramolecular forces are forces that hold together the atoms within a compound or molecule. So if we look at this picture down here, the bond is an intramolecular force. So bonds or chemical bonds are intramolecular forces. So if you think about intramurals, it's all students in a school playing against each other. So intra means inside of something. So the lines here are the bonds, and those are the intramolecular forces, or chemical bonds. These forces are extremely strong, or very, very strong. And in order to get these forces apart, or the bonds apart, the compound needs to undergo a chemical change. So without a chemical change, water is always going to be in water's form, or the compound. We're not going to be able to break those bonds apart. So they are very, very strong, and they're going to be the strongest things that we talk about today. And we should have written down this slide onto our notes. Now we're going to talk about intermolecular forces, and these are going to be the primary thing that we're going to talk about today. Intermolecular forces are other forces that compounds undergo or have, and these are called intermolecular forces. The difference here, if we look at this picture, there are two waters here that have forces that are happening between the two different water molecules. These are intermolecular forces. Intermolecular forces occur between different molecules or compounds. So we have two water compounds here, one right here and one right here, and because part of the water is negative, like we see with the O, that's a negative sign, and part of the water is positive, they're going to interact or attract each other because opposites attract. So these are intermolecular forces. So they happen in two different compounds that are very close to each other. Intermolecular forces, which is what we're going to talk about today, are not as strong as chemical bonds, which are intramolecular forces. So the bonds that we've been talking about, the covalent bonds or the ionic bonds that hold together compounds, are very, very strong. They are stronger than the other forces that we're going to talk about today. In this example, we have HCl, which is a covalent compound, and there's a strong force or bond that's occurring between the two different atoms to create the compound. We have another atom of H and another atom of Cl, so another compound. The forces in the middle are the bonds, or intramolecular forces. Those are strong. But the forces that are happening in between the two different HCl compounds are intermolecular forces, which we're going to talk about today, and they are very, very weak in comparison to the bond. But they're very important as well because they control certain things that we're going to talk about today. There are different types of intermolecular forces. Now you're going to be writing down this information on the table that looks like this. So the first kind of intermolecular force are called London dispersion forces. These occur in nonpolar covalent compounds, which are the compounds that you guys started talking about yesterday and also in the catalyst today. So nonpolar covalent compounds, which have a difference in electronegativity of 0.0 and 0.4 from that chart that we looked at, are the first type, and London dispersion forces are the forces that they have. These are very weak. Common examples of compounds that have intermolecular forces of London dispersion forces are CH4 and Cl2. The next intermolecular force we're going to discuss are dipole-dipole forces. These occur in polar covalent compounds. These are going to be a little bit more strong than the compound or than the forces that occur in a London dispersion forces, which are in nonpolar covalent compounds. And examples of these would be SO2 and H2O. If you ever need more time when I'm talking, you can just pause the video and then restart the video when you are done writing. The third type of intermolecular force are called hydrogen bonding. This type of bond only occurs in compounds involved with H and N, H and O, or H and F. So H needs to be involved, which is why it's called hydrogen bonding. And these are very, very strong intermolecular forces that are occurring between two different compounds of the same compound. Examples are NH3, so we have N bonding with H, H2O, which has O bonding with H, and HF, which has H bonding with F. These are the strongest type of intermolecular force. Then we have electrostatic forces, which are occurring in ionic compounds. These are not discussed as often, and an example of these are NAF. With any kind of ionic compound would have these electrostatic forces. So if you can see from the chart, we go from weak to strongest. And then I want you to remember that ionic compounds have have ionic bonds, and ionic bonds are going to be stronger than these intermolecular forces that we're talking about. So bonds are always stronger than intermolecular forces, but if you were to be asked a question about dipole-dipole forces, for example, and London dispersion forces, dipole-dipole are stronger because they're more polar. Hydrogen bonding are going to be stronger than our dipole-dipole forces, and so forth. Also, something to note is that hydrogen bonding can occur in either a polar covalent compound or a nonpolar covalent compound. So a compound can never have London dispersion forces and dipole-dipole forces, but they can have dipole-dipole and hydrogen bonding, or London dispersion and hydrogen bonding. So that's a possibility depending on the type of compound it is. So again, you're going to use this chart for your examples that we'll see in a second, and if you need help, then please raise your hand and ask Mr. T. So the first example that we're going to look at is CO2. So we are going to find the electronegativity for C and the electronegativity for O. So I found those on my chart, and they are 3.5 and 2.5, which I wrote down in this column here. The difference is 1.0. This means from yesterday that it's a polar covalent compound. And then looking at my chart, sorry about that, and looking at my chart, when I subtract them, we get 1.0, we get polar, and looking at my chart from today's class, if I look back to it, dipole-dipole forces occur when something is polar covalent. The next example is water. So water, we do the same thing. We find the electronegativities, and you should be writing this down in your notes. We find the electronegativities for both elements, and then we subtract them like you did yesterday with Mr. T. We're going to find out that it's polar, and that means it has dipole-dipole forces. But if you notice, hydrogen bonds are also listed underneath water, because water is a compound that has hydrogen bonds as well, because we have H bonding with O. So hydrogen bonds are much stronger, and they're a bigger force at play in water, or more important force at play. The last compound is LIF. I do the same thing. I find the electronegativity for both. I subtract them. When I subtract them, you see right here I get 3.0, which is an ionic compound. Ionic compounds have electrostatic forces. So if you need to pause to write this down, go ahead and pause. I'm going to move on. So the impact of intermolecular forces, this is about why it's important. Intermolecular forces have an effect on strength of forces, boiling points, and melting points. So strength of forces, boiling points, and melting points. So when we have a certain type of intermolecular force, it's going to impact the boiling point and it's going to impact the melting point.